Hi guys, we'll give it another minute before we get started. Just write a little reminder here.
Good morning.
Hi, how are you? So just some reminders. We'll give it another minute for other people to show up, but just some reminders to think about what's coming up this week. So we've got our homework, chapter 1.3, 1.4, that's going to be due tomorrow at midnight. Our classwork also for 1.3 and 1.4. Remember, we've actually been over a lot of the classwork already for 1.3. There's a couple of problems I want to do. I missed them last time, so I'll go over those. 1.4. We're going to do 1.5 today, but 1.5 stuff I'll collect next week. So I think I changed that on our changed the due date on that. Tomorrow we have a quiz on 1.3 and 1.4. The quiz, just like last week, is going to be available from noon tomorrow until noon on Friday, but it's a 30-minute quiz, so that should be there. And I just want to ask you guys really quick, I had the problem in my other classes where I graded the quizzes and the homeworks and stuff, and then I had the grades up on the grade book, but they couldn't see them, right? You guys should be able to see the grades as well as like comments that I would have written on top of the quiz. And the rubric, like how many points I took off on which problems and stuff. Is everybody able to access all that on the grade portal and see the feedback on your quizzes? Let's see, I'll open up my chat here.
I never checked it. Sorry.
Yeah, that's okay.
Yeah.
You know, I'm not putting anybody on the spot. You guys can check it later and then let me know or send me an email. I think one of my students in my earlier class told me that she had to go into Speed Grader and then look at like the rubric. Maybe there was like a certain set of words or something she had to play around with in order to see my comments on there. It'll become more important as we get closer to the midterm exam, which is coming up in a couple weeks. And then so that you guys, you know, have all that stuff to study from. All right, so very exciting stuff today. We are going to start chapter 1.5, which is really cool stuff. So we did, chapter 1.4 was about cross product, right? Which was taking in two vectors and multiplying them together. And when we take in two vectors, we get a vector output when we do the cross product. If we use the dot product, we take in two vectors and we get out a scalar. Okay, so cross product and dot product have two different mechanisms, right? And they're used for different things. So today we're doing chapter 1.5, which is very exciting. And we're going to start talking about what we call implicit equations for lines and planes. We'll talk about what I mean by implicit in just a minute. Okay, so we're going to describe lines and planes. We're going to start off with lines. It's a little more simple, and then we'll expand our approach into planes. Okay, so before, up until now, like in algebra, like you talked about y equals mx plus b. And then in the earlier chapter, we said, well, let's change that. We'll take it out of the coordinate plane and we'll represent it with a vector equation, right? Which was x bar equals x naught plus t times v, right? Where x naught was a point on our line, t was a parameter, and v was a vector that was parallel to that line. So let's draw it out like this. So I've got, here's my x naught, that's my point on my line. And I've got some kind of vector here. Here's my v, my vector that's parallel to that line. Okay, and then we say, you know, this is, you know, x bar. X bar is any particular, it's a general point on the line. It's like when I say y equals mx plus b, only the m and the b are defined, right? And then the y and the x, I can choose the x values and I can get out a y for it. So this is what that means too. That's a sort of a general, you know, definition for it. This is like our x, y. Okay, and we'll say this is our, what we call a equals x. All right, now what I want to start talking about is an implicit equation. Says we're not going to be representing things in terms of like, I'm not going to have like say a t and a v anymore. I'm going to take it away from representing my t values, okay? But what I need in order to do that is I need something else. So what I need for that is I need a vector that's perpendicular to that line. I'll call that u. Let's write down what that is. So u is a vector perpendicular, right? Which means it's at right angles. Line. We say it's orthogonal to the line, and we say it's normal to the line. All of these things, perpendicular to the line, orthogonal to the line, normal to the line, those are all synonymous with each other. Yeah, perfect. Okay, so I need to be able to figure out how I'm going to get that, right? And then what I want to do is I'm going to use that vector u to write this equation of the line. Use u, equation of the line, right? And ultimately also my plane. And then this means that we won't have no need for parameter. Right now, I could take it, which is like implicit. I'm implying that there's a parameter there, but I don't need it specifically because I'm going to use my u value. Okay, so let's talk about what u is and how we actually get it. So u, I'm going to say it has an a and a b, my x and a y. We're going to start off with 2 dimensions, an x and a y component. Okay, so this is u sub x, u sub y. Right, so these are my, that's a u, sorry, it's a u sub y. So u is a vector and it has an x component and a y component. Okay, now let's think about what's going on. I'm gonna kind of derive it. This is, we'll say this is orthogonal to our line. Okay, so I'm gonna come up with how I actually get that, but bear with me here as I work it. So if I say, if it's orthogonal to the line, that means I can go u dot product with v to be equal to 0. Remember, v is the vector that's parallel to the line. Right, that's our vector that's on our line. It's this one right here, right? That's the one that we use to describe our vector equation. So now if this is really the orthogonal, it's a normal to that line, u dot v dot product is going to be equal to 0. So I'm going to exploit that. So v, I can also say v is a displacement vector. Remember how we did that?
Is that a v? It says, remember, v is vector parallel.
My v, where v, yeah, v. This, you'll know v's and u's are different. I can't make it really pointy. I'll try to make it as pointy as I can, but the u is going to have a little hook on it, and the v won't. Yeah, I know. We'll have a quiz on my handwriting, you know, later in the semester too. But right now, right, u will have a hook and v won't. But I'll try to make them as pointy as I can. So displacement vector, I can define v as a displacement vector. Remember, so I can say I'm going to go I'm going to say any particular x point minus my x naught, right? So this is my xy, right? So this is xy minus x naught, y naught. And that was how we calculated our displacement vector. I said I have 2 points on the line, right? I subtract their x components and I put it in my x location, subtract their y components, put it in my y location. That gave me my displacement vector, okay? So now I'm kind of coming up with a generic equation for that because I'm going to substitute this in for v here because I'm using this to help me derive, like to explain this implicit equation for my line, so u dot v. Okay, so now let's substitute that into here. So I'm going to write that down here. So I'm going to go u dot product with, right, I'm going to spill this out here, x minus x naught equals 0. Okay. Remember our properties of dot product, I can distribute this dot product u dot x minus u dot x naught equals 0. Okay. X naught is a specific point. That's like 3, 4, right? X bar is my generic x comma y, okay? So let's remember x naught is specific numbers, x bar are x comma y, okay? Because that's important. We're going to plug those things in. So this is, right, using my dot product to do that. I'm going to turn the page. I'm running out of space here. You guys all have this before I turn the page? Give it a minute. Let me know when you're all set. Okay, I'm going to turn the page here just because I was running out of space. Okay, so let me rewrite that. So you said u dot v was 0, and I substitute, oops, so u dot, this was x bar minus x naught equals 0, which I then wrote as u dot x bar minus u dot naught equals 0. Okay, I just rewrote it so I can have it here when I go to do it. All right, so now, okay, what I'm going to do is I'm going to put the component pieces into here. So that means I'm going to write it like this. So u sub x, u sub y dot, let's do this here. This is x comma y minus u sub x, u sub y dot x naught, y naught equals 0. Okay. And remember, u is a vector. Like maybe we actually have that vector where we were given that, right? So what I can do is I can add this to both sides. So this looks like u sub x, u sub y dot x comma y equals, right? I just added this term here to that side. U sub x, u sub y dot x naught comma y naught. Okay. I'm deriving this implicit equation here. Now I'm going to take, remember our dot product is I multiply corresponding components and I add them up. This is going to be u sub x times x plus u sub y times y equals ux x naught plus uy y naught. Okay, this right here is a constant term, right? It's just a number, okay? Because like u of x, u of y, these are just numbers. This is a vector. Vector has like 2, 3, and my x naught, y naught, that's a point. That's a coordinate. 3, 4 we said, right? So when I do a dot product of these numbers, I'm just going to get a scalar here. This here, x and y, right, are variables, x and y, that stay as variables, x and y. So now I have an equation, right? So basically what this looks like is, right, I'm going to call this u sub x times x plus u sub y times y equals some constant. Okay. So this looks like, I'll write it, make it look nicer. So if I can say that I'll call this ax plus by equals c, where I'm just like substituting in a for u sub x and b for u sub y, so it looks prettier. Okay, but this is our implicit equation for a line. Okay, it's implicit because I'm implying that there's a parameter there. And it requires a vector that's orthogonal to the line. So my u, oops, that right? Which I called a comma b just because I'm trying to make it look prettier, right? So this is my vector perpendicular to the line, okay? So the coefficients for x and y on my implicit equation make up my normal vector, okay? C is a constant term. We're going to do examples so that you can see it. It's implicit. Implicit means there's no parameter. This was our t specified. It's implied in the line. Okay, so the vector equation uses, we'll summarize this, the vector equation so our vector, which is our parametric equation, uses a vector parallel to the line. Right, this is our line. This is our vector, x naught. Okay, that's one thing to note. The other thing to note is that the implicit equation uses a vector normal, which is perpendicular to the line. So if this is our line, this is our normal vector. This is x naught. Okay, two different things, right? They represent the same line equation. I need to be able to work back and forth between each of these here. Okay, we're going to need both of these representations for different things, and we'll see why as we go. Okay, so this one is, let me write this down in red. This is x bar equals x naught plus t times v. This one is ax plus by equals c, where a comma b equals our normal vector. Okay. Implicit versus vector equations. Okay, it's the same line, different ways of describing it. They have their uses. They have definitely reasons why we would want them, and we're going to use them interchangeably. We'll see why as we go along. We'll see why which one is important. We'll do some examples so you can see what I'm talking about here. So I got my lecture example page for chapter 1.5, and I'm taking a look at my example number 1. So this one says you want to find an equation of the line in R2 which contains the point, so this is our x naught, and is perpendicular to this vector here. Okay, so that means, so our line, right, has the point 1, -3, and it has the vector 5, 2. So watch how it's being worded. It says our line is perpendicular to the vector. So if that's the vector that's perpendicular to the line, right, I have my perpendicular, I have my point, okay, and now I can start plunking it into my equation, okay? So let's do this. So there's a generic equation for our line, and it goes like this. A, this is my x component of my normal vector, x minus x naught, plus b, y minus y naught equals 0. And let's write out what these things are. So a and b are the normal vector components, okay, which is what we've been calling u. X naught, y naught is our point on the line. Okay, and then x and y, without like the little 0 on it, x and y is our generic point on the line. Those are like, I choose a point on the line, I plug it in, and it's gonna, generate these different, it's gonna generate the whole line. So X and Y are generic. Okay, so now we were given, right? So my A and B is equal to 5, comma 2. I was told that my line is perpendicular to this vector right here, okay? And we were told X naught, Y naught is equal to this point 1 minus 3. So I'm going to plug that into here. We're going to do this a couple ways so that you can see how else we can do it. Okay, so I'm going to plug these into my equation. So A and B and X naught and Y naught are going to go there. So 5 is my A, X minus 1 plus 2 is my B, Y minus a minus 3, and that's equal to 0. This is one way of writing it. I'm going to multiply it all out so you can see how it'll look like AX plus BY equals some number. This is going to be 5X minus 5 plus 2Y plus 6 equals 0. All I did was distribute these terms to here. Now I'm going to combine, so I'm going to get 5X plus 2Y minus 5 plus 6, right? This is plus 1 equals 0, which I can then write as 5X plus 2Y equals a minus 1. These two are the same line. They're just written differently. Okay, they're both correct. I'll take both. Okay, this also, you can write your line equation instead of bringing the one over to the other side. Either one is totally fine. Okay, so using the dot product method, right, when we first derived our line, we used the dot product. I can do that to help me figure out the line too. So I can say U dot X equals U dot X naught. Okay, and I can use this to help me generate the line equation. So U, that's my normal. This is going to be, we were told that's 5 comma 2 dot, this is X, Y. This is my generic X and Y. U, so this is 5, 2 dot, the point on the line. So we were told the point on the line was 1 minus 3. So I'm going to take the dot product. So that's going to be 5X plus 2Y. Remember, dot product is corresponding components, multiply together, and then I add them all up. Equals dot product here with just numbers. So 5 times 1 plus 2 times a minus 3 becomes 5X plus 2Y equals minus 1. Right, we get the same equation. We should get the same equation. Different methods for getting there, they're both correct. I'm going to let you choose which one you like the best, and then I'll let you choose which one you want to do. Okay, they're both correct in terms of generating the implicit equation for that line. Okay, I'll give you a minute to finish writing all that down. And we'll do some more examples. You guys all set? So let's take a look at example 2. So example 2 says, find the implicit equation for the line that goes through the point 2, 1. So we're given this is X naught, Y naught. I like to take notes when I'm reading a problem. And is parallel to the vector 3 minus 1. Ooh, so we have to be careful. So this is our vector V, right? So we are given, this is X naught, Y naught, and we're given a vector that's parallel to the line. Okay, so there's like a trick on here. All right, so our vector equation, which isn't what we were asked for, but we're going to write down. Our vector equation is X bar equals our X naught plus T times V. So X bar equals our X naught, 2 comma 1 plus T times our vector, 3 minus 1. Okay, so we need to come up with an implicit equation, which is AX plus BY equals C, where A and B are the u. So I need to come up with a u. There's a trick I'm going to show you. Okay, so to get our vector that's perpendicular, vector perpendicular to the line from the vector that's parallel to the line, which is our v, okay? What I need to do is this. I'm going to, okay, so I take v and I switch the x and the y components. Okay, so let's write that here. So I switch the x and y, so I take v. So v is equal to 3 minus 1. And I switch the x and the y components. So I get 1, 3. And then after I do that, I negate the value, the new y value. Right, so 3 becomes a minus 3. So this becomes minus 1, minus 3. Okay? So this is perpendicular to this. It's a trick. There's a reason for it. I'm not going into the reason for it, but it comes from like algebra and stuff. Okay, so now let's think about our vectors. So if I have a vector, so here's my v, and then here's my u. Let's draw it like this. So u equals minus 1, minus 3, right? And that's perpendicular. What happens if I multiply u by minus 1, right? If I multiply u by minus 1, look at what happens. This is minus u, which is going to equal to positive 1, positive 3. This vector is also perpendicular to v. So minus 1, minus 3 is perpendicular to 3 minus 1. But so is 1, 3, perpendicular to 3 minus 1. Okay. What happens is we tend to like to use things without so many negatives because sometimes we can forget our negatives when we're doing our math, right? So I'm going to use this one, this version. It's also perpendicular to my line, right? So I can use it. It's a perpendicular, it's a normal to the equation. All right, so now I've got 1, 3 as my normal. So my normal vector, 1, 3. Okay, so now I'm going to use that on my equation. So I'll do the dot product method. So we can see both interchangeably. So I'm going to go, this is going to be, let's draw it out. So u dot x equals u dot x naught. So that's going to be 1, 3 dot x y equals 1, 3 dot the point on the line, 2, 1. The point, it's the same point, right? So I don't have to do anything weird to the point. The point is still on the line, okay? Just my normal vector that I'm looking at. So now I'm going to dot product this out. So I'm going to get 1 times x plus 3 times y equals 1 times 2 plus 3 times 1. So my equation is 1x plus 3y equals 2 plus 3 equals 5. So this is the implicit equation for our line. Okay? Implicit equation for the line, vector equation for the line. We were asked for the implicit equation for the line. So that's what we just did. But there was a trick. I was given the vector parallel to the line. I had to find the vector that was perpendicular to it. Switch the x and the y, and I negate the new y. I'm going to talk about planes for a little bit, and then we'll take a break. We should still have like 20 minutes or so in which to do classwork. I'll give you guys a chance to finish writing this, and then we'll talk about planes. All right, so let's talk about planes. So in 3 dimensions, we want to describe a plane with an implicit equation. Remember when we did our vector equation for a plane? I had a point, I had 2 vectors, and they had 2 parameters, 1 for each vector, okay? So let's just draw pictures so we can see what this is going to look like. Remember, our planes are infinite, but I'm just drawing it out like this. So here's our plane. So imagine, right, I've got this vector x. Now imagine I have my vector u. My vector u, which we sometimes also call n, you know, it's a vector that's normal to the plane, okay? Here's our point A. So let's do this. I'm going to say x minus a is our displacement vector. That's on the plane. Okay. U is the vector normal to the plane. Right? It's perpendicular to our plane. Okay. And then we can call this, it's got components A, B, C. Okay. Right. So I'll say A is our point on the plane. And I'll say this has AX, AY, and AZ. Remember, 3 dimensions, so I need an X, Y, and a Z component, right? And then X is my generic point, which is X, Y, Z. We're going to derive our equation kind of like what we did before with our dot product. So what I'm going to say is my U vector, I'm going to go U dot X equals U dot A, just like we did before. Okay, so I'm going to fill in the blanks here. So U is A, B, C. I realized that I probably should have done a different variable for my point. X, Y, Z equals A, B, C dot AX, AY, AZ. Okay. Now I'm going to dot product these out. I'm going to get AX plus BY plus CZ equals, this is a constant term, A times AX plus B times AY plus C times AZ. And since we're already using A, B, and C, we'll call this D. Okay. So what we do is, to write our implicit equation for a plane, I say it's AX plus BY plus CZ equals D. It's implicit because my parameters are implied, right? I don't have a parameter, but I'm using the vector that's normal to the plane, right? That's my U, to describe my plane equation. Okay. I can also do it if I'm given a point, my generic. It's going to look like this: A, x minus x naught plus b, y minus y naught plus c, z minus z naught, and that's equal to 0. The d comes from a times x naught plus b times y naught plus c times z naught. I add them all up, right? It's my constant term, just like what we did right up there. Okay, but my generic, this x naught, y naught, z naught is a point on the plane. X, y, and z is my generic point on the plane. A, B, and C is my normal vector. So again, the coefficient of x, y, and z, coefficients of that form our normal vector. So if you're given an equation for a plane, you can just pull out the coefficients for x, y, and z, and that will be the vector that's normal to your plane. Okay, so I'm looking at my, all right, great. Okay, so this is nice. We'll do example 3. We'll end on example 3, and then we'll do a bunch of classwork problems. Example 3 is a really nice. This is a common question that we like to think about. So we've got 3 points. Want to write what's some books call it a standard equation. Some books call it an implicit equation. We're going to use those terms interchangeably, right? A standard or implicit equation for a plane containing these 3 points. We want to find the area of these triangle with these 3 points as vertices. So that's kind of a hint about how we're going to be solving part A. All right. So the first thing I want to do is I like to kind of visualize. So I'm going to draw a plane. Here's my plane. Right. And I've got my points A, B, and C. Okay. These are points that are on the plane. Now, remember, like we did before, I need to come up with my vectors, right? My displacement vector. I'll call them B and W. Okay. And then I'm just going to remind us. I'll call this one N for normal. Okay. So remember what we do, right? I calculate out my displacement vectors, V and W. Now, if I have 2 vectors and I want a vector that's normal to both, I'm going to take the cross product, and that's going to give me a vector that's normal, orthogonal to both of those vectors. We're starting to pull together all the different things that we've been covering so far in this chapter. All right, so let's calculate our displacement vectors. So V goes from A to B, point A to point B, which remember is terminal minus initial. So B is 2, 1, minus 1, minus A, 1, 0, right? Terminal point minus initial point. So B is equal to 2, 1, minus 1. A is equal to 1, 0, 1. So my V, my displacement vector V is 2 minus 1, 1 minus 0, minus 1, minus 1. That's my first displacement vector. W is going to go from A to C. Remember, if I identify A as my initial point, it has to be the same initial point for both displacement vectors, or the math is going to come out wrong. This goes from A to C, which means I'm going terminal minus initial. Okay, so I'm going to fill in the blanks. C is equal to 0, 3, 0, minus my A, 1, 0, 1. Okay, so I'm going to calculate these out. W equals, and you can use whatever variables you want. I have V and W I tend to use a lot. 0 minus 1, 3 minus 0, 0 minus 1. So I have my 2 displacement vectors. Okay. We're working our way through it. Now, I need to find these 2 vectors, by the way, are on the plane themselves. So you can think about our plane. Think about it as a piece of paper. Here's my plane, right? I have a vector V, and I have a vector W. They're both on the same plane, okay? So I need to find a vector perpendicular to the plane, which will make it a vector perpendicular to both V and W. So how did we find a vector that was perpendicular to 2 incoming vectors? I took the cross product. I'm going to say my normal vector is equal to V cross W. Now, by the way, it doesn't matter if I do V cross W or W cross V, because you can imagine, right, this is negative N, right? It's the same, it just is pointing in the opposite direction. So it'll be fine either way, whichever N you choose. So if you do V cross W or W cross V, it doesn't matter, because I'm still generating a vector that's perpendicular to the plane. All right, so V cross W, I tend to go in alphabetical order, I, J, K. So I'm going to go 1, 1, minus 2, right? So this is my V. Minus 1, 3, minus 1, that's my W. Remember your order, I, J, K. Okay, so I have to generate first row, first column. I make up a matrix minus J. First row, second column, I ignore them. Make up a matrix of what's left over. Plus K. First row, third column, I ignore those and I make up a matrix. Okay, now I'm going to do my little cross product on the inside here. And I subtract those, right? So let's set that up. So this is going to be I times, this is 1 times a minus 1, minus 3 times a minus 2, minus 6, minus a minus 6 gives me plus 6, minus j. So this is 1 times a minus 1, minus 1 times minus 2 is positive 2. So I'm going to go minus a positive 2, plus k. Watch your negatives and whatever. So this is 3 times 1, minus a minus 1. So this comes out to be minus 1 plus 6 is 5. This is minus 1 minus 2, so that's minus 3 times a minus becomes positive 3. 3 plus 1 is 4. Okay, so I found a vector that's perpendicular to both displacement vectors, which means it's perpendicular to the plane. I took the cross product. Normal. Okay. Now I can generate my implicit equation because I've got my normal, right? And I have a point on the plane. So point on the plane, I can choose any one of those points that I want. I like to look at C because that's got a lot of zeros in it. Every time I see a point that has a lot of zeros in it, I like to use it because 0 times something is nice. So I choose that as my point on the plane. So I'm going to go n dot x equals n dot c. And it's going to generate my implicit equation. Fill in the blanks. 5, 3, 4 dot x, y, z equals 5, 3, 4 dot 0, 3, 0. Okay, so this is going to become 5x plus 3y plus 4z equals 5 times 0 plus 3 times 3 plus 4 times 0 equals 9. This is our implicit equation of the plane containing the 3 points A and B and C. 3 points given. Okay, that's part A. Okay. Part B said, what's the area of the triangle with A, B, and C as vertices? Remember how we did that area of the triangle. It's going to be 1/2 the magnitude of my cross product. Right? Remember, the magnitude of the cross product gave us the area of the parallelogram, right? That would be this parallelogram right here, right? But we're going to calculate this 1/2 of it. We're going to calculate the area here, that triangle. Okay, that's what I'm looking for, the area of that triangle. So I take 1/2 the area of that cross product. So that's 1/2 magnitude of the vector 5, 3, 4. That was my cross product, right? So I got to calculate that magnitude. Don't forget to divide by 2. So that's going to be 5 squared plus 3 squared plus 4 squared. Add it all up, square root it. Okay, so we're looking at 1/2, 25 plus 9 plus 16 is radical 50. You can leave it like that, totally fine. Or you can simplify it and get 5 radical 2 all over 2. Both of these are correct. I'll take either one. Okay. A lot of new stuff, but exciting. I'll leave it up there for you guys to finish copying. What I'd like to do is I'm going to start working on the screen. On the classwork for 1.3, there were some pieces that I forgot to do. That was the back of one of the classwork pages. It had like a graph, and then we wanted to figure out what its vector addition was, and then we wanted to do a dot product and other stuff. So I have that here. I'll work through those here. Then I also have classwork for 1.5. But I'll work through this one first. Okay. And I'm still trying to figure out breakout rooms on Zoom. If you guys have an interest in doing breakout rooms for classwork, or you just kind of want to watch? Yeah, okay, we'll figure it out. You guys can let me know. All right, so I'm going back to classwork for 1.3 just so that I can pick up 1.5 again tomorrow. And so let's do this. So I'm gonna, this is a 1.3. The classwork looks like this. It starts off with this at the top. And we did part of it the other day, but I realized I had forgotten to do this part of it here. So I'm gonna do these. So I'm gonna set up an axis here. I have to specify the origin myself. So we can see the parallelogram rule. This goes back to earlier chapter section, but I plotted u, 2 minus 3. I plotted v, 4, 2. And then their sum was 6 minus 1, was out right here. You can kind of see how that would actually be, right? The diagonal of their parallelogram. Okay.
Which classwork is this?
This is 1.3. I went back because I realized I didn't do it in class. And so I wanted to do it here for you guys. And then this one here has multiple ways of doing it. So so we've got u.
Was that part 1 or part 2?
That's a good question. I don't remember, but it looks like this at the top.
That's part 2, I think.
Part 2.
Oh no. Actually, I
Part
don't
1.
know.
I don't remember. I have it listed like that on my the title of my file, but not on the page itself.
No, that's part 2 because I think part 1 only had 4 questions.
Okay.
Yeah. And I had a question about number 4 on part 1 when you're done.
Okay. Yeah. Let me finish up this page here, and then we'll talk about the other stuff.
Thank you.
How many you said, what was it that you had a question on? 1.3?
1.3, question 4.
Then, is it a projection question, vector component of U along A?
Yeah.
Okay. What's your question? What do you want to talk about?
I just got confused about along. That's
yeah,
why.
like the word, right? Yeah. So I'm trying to use wording that's we say projection in our class, it's projection in other classes. Other textbooks also use the term the vector component of U along A, which is like the projection of U onto A.
So it's
if
the
you can
same
think,
thing.
it's the same thing, just different words. And then the vector component orthogonal to A. So that's like we're saying, you know, I've got, if you can imagine a projection, right? I've got, here's my A, here's my U, right? And if I project onto it, here's the projection of, you can't read my writing, the projection of U onto A. So it's like I am doing that component of U that sits along the A vector, right? And the part that's orthogonal to it is my normal, which is just by vector addition, right? I'm gonna subtract, you know, U equals, U equals the orthogonal plus the projection gives me my U. So I can then subtract them from each other and then get my orthogonal. That's all that that means. It's just finding the projection and then the part of the projection that's perpendicular to it.
Okay. Thank you.
Yeah.
That's it. Yeah.
Okay.
I just didn't know what it meant.
I know, right? I'm trying to use all the same word, the different wording so that you can, you know, see what it means. But I'll leave this up here so you guys can see what I did. Give it a minute and then I'll. And I think I will do the classwork for 1.5. I'll do that tomorrow just so you can see what that looks like tomorrow. Question number 5 on here, I did it a couple different ways. I did just the regular dot product of the two vectors, and then I also did with the cosine. You want to make sure that you are you know, fluent in both because this one has the cosine. You need the cosine in order to do that one.
On the homework, to which question were we working to?
Let me look at my syllabus. Give me just a sec. I think it goes up to question 12. Up to question 12. So you're basically doing 9 through 12 because we did, I think, up to question 8 last time. Was that true?
Yeah.
So you're going to do 9 through 12. I think question 12 is on the syllabus on that main page.
Oh, okay. Okay.
And I have office hours today too, if you guys have any questions you want to ask. Okay, so leave that there. If you guys don't have any other questions, then I'll let you go. And then if you want to come to office hours, you're free to come to office hours and ask questions. Tomorrow we will pick up and finish off 1.5, and then we'll probably end early, and then I can work through some examples. I can answer some questions, and then you guys are free to get ready for the quiz. Okay. Okay, bye guys. Have a great day.